Okay, good day, ladies and gentlemen. Welcome to our lesson. So today we're going to be looking at this reactor problems for this tutorial. Now, basically, we're going to look at how do we get the volume if we're given the data, the volume for a PFR reactor, and also for a CSTR, and also how do we get the overall volume. Now, we're going to start by viewing what we're given on the statement here. As you can see, the irreversible, let's do question 1. Okay, the irreversible gas phase non-elementary reaction is to be carried out isothermally. Okay, that means at constant temperature in a constant pressure batch reactor. So it's constant temperature and pressure. So the feed is at a temperature of 300 degrees Celsius and a pressure of 101,325 kilopascals. Okay, there's a correction there. It's supposed to be 101.325 kilopascals. Okay, 101.325 kilopascals. Okay, and its composition is 40% of component A and 60% of component B. Laboratory data taken under identical conditions are as follows. So now you're given the laboratory data here. First of all, you're given the chemical reaction equation, and then you're given the table with the laboratory data. Now, the first thing that you are supposed to do, or what you're required to do, is to estimate the volume of the plug flow reactor. Estimate the volume of the plug flow reactor required to achieve 40% conversion of species A or component A for an entering volumetric flow rate of 50 cubic meters per minute. Now, how do you go about doing that? So the first thing that I always advise was also important, just make sure that you sketch so that you can actually see what you're talking about. So now if it's a plug flow reactor, you just sketch. Okay, this is a tubular reactor. So it's a tubular reactor. So now in a tubular reactor, that becomes FAO, and that is FA. Okay, this is the entering flow rate, and this is the initial flow rate. And then after that, what you can do, you're given the chemical reaction equation. Species A react with species B, giving out species C. Okay, so that's how your chemical reaction equation looks like. And also you are given the initial conditions. Okay, so initial conditions, I'm talking about the initial temperature, which is given by 300 degrees Celsius. Can add that to 273 because we are using absolute temperature. That will give out 573 kelvins. Okay, and then you can also go about and look at the other condition that you are given, which is the initial pressure, also standard atmospheric, so it's 101.325. so that's constant pressure and temperature, it's kPa, kilopascals. Okay, and then the other thing that you given is your initial molar flow rate, okay, of species A, which is 40, okay, 0.4. and then lastly, what you're given, you are given initial flow rate. Okay, the initial flow rate is 50 cubic meter per minute. So you're given all those components there to help you solve the problem. Okay, so that's what you're given. So the first thing that you're going to do, once you have these different factors, okay, once you have these different factors, you are going to find a way on how to find the volume. So the volume of a PFR, or the volume of a PFR, let me just do this. Okay, volume of a PFR, can remove that now. PFR, which is a plug flow reactor, is given by FAO Okay, and then you've got the limits from initial conditions to the specified conversion, and then you've got the integral px minus Ra. Okay, so the Ra is the rate of reaction. Ra is the rate of reaction. So now this is interesting in how we're going to solve it. So we have to create more space. So how do you do that? We create more space. So let's look at it in detail and see what we come up with. Okay, so now we're going to start with the integral and apply Simpson's rule. Okay, we're going to start with the integral only and apply Simpson's rule. 0, these are the limits. Okay, dx. For now I've taken out FAO. Okay, so that there's no confusion. Rate of reaction. So, and then Simpson's rule gives you this formula. This is the interval change in x. Okay, between the conversions. Okay, and then you've got negative Ra, which is the rate of reaction. Now remember, A is disappearing in the reaction, hence the negative sign. Now open brackets, you've got FAO. Just write out the rest of the formula. Okay, the rate of reaction here, and then these are the initial condition where x equals to 0. So initially conversion is 0 because reaction hasn't taken place, and then as the reaction proceeds, then you'll see the values in the conversion. This is negative Ra, and then here you also have x1. Okay, and then got the other reactor, other reaction conversion. So here the point x2. Okay, so this is how it looks like. Now it's very key, okay, that you understand, because now we'll be substituting in the formula. Okay, so now we substitute in the formula. Now we put up the values. So we've got the values here. The interval is 0.2. Okay, now 0.2 is the interval between the given values, okay, of conversion. If you can check, this is what we're talking about. So this is 0, 0.2, 0.4, okay, and there you've got another value there as well. Okay, so the intervals that are given, so that's very, very important as well. Okay, so now let's proceed with the question. Okay, proceed with the question. So we've got 0.3. Okay, and then here you've got 3. I think there's an error there, so erase that. This is the interval, and then here there's 3 because it's Simpson's 3-point rule. Okay, so it's the interval, the change, and then divided by 3. Then you've got these 3 values. So now 0.2 divided by 3, and then you substitute the corresponding values. So at x equals to 0, you've got the value or the inverse of the rate of reaction given as that 1.67. So you're given the inverse there. So when you write it, you're going to write it as a normal number. Okay, and then plus 4 times 3.33 times 10 to the power 3 plus, okay, and then here what you have, you're going to have, just open up so that you create the space. Okay, so here you're going to have 8.33 times 10, okay, to the power 3, and then you close the brackets. Okay, so now when you work that out, you're going to have the value of 0.2 divided by 3, and the brackets you work out 23320. Okay, and then that can be simplified to 1.5 when you calculate to your calculator, 4.67. Okay, so now you've sorted out the integral. So things become easier once you've done that. You've sorted out the integral, and then what you can go and do is to find the value now of FAO. Okay, finding the value of FAO. Okay, so now how do we find the value of FAO? Now we know that FAO is given by initial concentration multiplied by the initial volumetric flow rate. Now we have the initial volumetric flow rate, but we do not have the concentration, initial concentration. So first of all, we find the initial concentration. So initial concentration is given by initial, let me just remove that. Okay, so the initial concentration is given by the initial mole fraction multiplied by initial pressure multiplied by reaction constant rate, the rate of, and then also the temperature. Okay, constant rate and the initial temperature. So we have all these values, and therefore we can be able to calculate the initial mole fraction is 0.4 multiplied by the pressure, which is 101.325, okay, divided by everything, that is 8.314 reaction rate constant, this one is given, and then 573. Okay, so the universal gas constant. Okay, so that's the universal gas constant, and then from there we're able to compute, okay, the answer. We're able to compute the answer there. Okay, so if you're given, so we should get something like 0.0085. okay, that is your initial concentration. And then moving forward, for you now to find the FAO, which is your initial flow rate, it's going to be given by the initial concentration, which is 0.085, okay, multiplied by initial volumetric flow rate. Initial volumetric flow rate is 50, and then we just say multiply by 10 to the power 3 to convert it to decimeter cubed. Okay, we open more space. Okay, and then what we're going to have here is slightly different. Okay, so equals to, okay, so what you get here now, and the value that you have is 425. That's your initial flow rate that's coming into the reactor, the tubular reactor. So now, because we have all these values there, we can say finally our PFR, what we're looking for, the volume of the plug flow reactor. Okay, since it's FAO multiplied by the integral, just got limits, okay, dx, using the conversion, negative RA. Since now we've dealt with the integral and also dealt with FAO, we can easily work out the answer. So here we've got 425 multiplied by 1554, okay, 0.7. And then what do we arrive at? Create space. So once we've done that, this is what we arrive at. We're going to get our final answer now becomes 6614. Sorry, it's 66. Just erase that one. Okay, 661 0.345. Okay, so 661,345.7 decimeter cubed. Okay, so that's the volume of the PFR. The volume of the PFR. Okay, so once we figure that one out, now we are required to find the volume of the CSTR. Now the volume of the CSTR, okay, it's not going to be difficult. Okay, it's straight to the point. So now what is it that we do? So the volume of CSTR, which is continuous state tank reactor, okay, is given by design equation FAO multiplied by the conversion divided by the rate of reaction. Okay, so now this one is the same as FAO. Okay, now since we've got these values up there, if you can check, okay, this is where we get the values, because I know sometimes it can be a bit disturbing in terms of where we get the values. Okay, so we get the values from this table here. Okay, that's where we get the values from this table, and you can see this is the inverse now, the inverse of density. This one here is the inverse of the rate of reactions, or rather, and then since we want to find the volume here, the first one here, it was x, oh, that's a conversion, x1, x2, okay, and then x3, okay. Yeah, so now we're going to deal with x4 and x5. Okay, yes, so it's very important for us now to line it up so that you are able to actually get the right answer. Okay, so x5 minus x4. So let's go back now and try and solve a problem. We just remove that. Okay, and then we just go back. Okay, see, this is what we've solved, this is what we've done. Okay, so that's where we are. Okay, let me just make sure that I broaden that, and then I'm gonna bring back the marker. Okay, so now, so you've got x5, okay, x6 minus x4, okay, and then all over as RA. Okay, so now here we just have to populate this with values. FAO, now remember, this are just, okay, this is just what we're given. This is just what we're given. Let me just remove this and open more space so that we're able to actually solve it without any issues. Okay, there we go. Yes, okay. Okay, so now FAO we're given already, so we just need to write the values now. Okay, we just need to write the values. So now when you write the values, FAO is 50 multiplied by 10 to the power 3. Remember, we're using decimeter cubes. Multiply by 0.0085. Okay, and then we've got 0.6, subtract 0.4. Okay, and then multiplied by the value of 16.7 times 10 to the power 3. Okay, because that's the conversion. Okay, it is taking place at 0.6. So now these are the values that we have. Okay, and then all over that. Okay, so that's how you're going to compute the volume. Okay, so the volume here, you can just check it. 14,195. Okay, so it's 14,195 decimeter cube. You work it out, and then to total up everything, so this is the volume of the CSTR. This is the volume of the CSTR, and then the total volume that's required in C is going to be given by the volume of the PFR and the volume of the CSTR. Okay, and then you can actually compute the total volume. Okay, so that's how you figure out the first question. Okay, and then as we proceed in the second section, we'll solve the second problem. Okay, and that's going to be dealing with equilibrium conversions and see how do we actually handle that. Thank you so much for watching. See you in the next question.